All right, this next example we have is example 2 to rotate. So there's a little addition here. I want to make sure we add this in. These notes that I wrote are kind of old. They need to be edited in for typos and clarification. This is one problem where there really should be a little bit more written, I would say. Um, so I'd say rotate, and then I've insert right here the region enclosed by x equals 0 and x equals y squared about the y-axis for y between 0 and 2, and determine this volume. So first thing we do for any volume revolution problem is we should sketch these graphs. So also I want to quickly make mention of the fact that we have to do this for y between 0 and 2. And this x equals y squared, it is a parabola that opens in the direction of positive x, so it looks like that. But because we're only interested in the portion of it between y equals 0 and 2, there's no point in sketching the full thing, so let's just sketch this. And also, if you didn't know what this looks like, you can argue that the fact that the coefficient is positive, it's going to open in the direction of positive x and go from there. All right, so then we've got y equals 2, or sorry, excuse me, y equals 0 and y equals 2. So y equals 0 is already sketched. That, of course, is just the x-axis. So if I label my axes, then this would be y equals 0. And then y equals 2, that isn't sketched, so there's y equals 2. Okay. And then the and x equals 0 is the y-axis. So it looks like we have boundary, boundary, boundary. So that encloses this region right here. Okay. And we are rotating it about the y-axis. All right. So to do this, because we're rotating about a vertical axis, that means our volume integral, which is pi times the integral from a to b radius squared, this would be with respect to y since we're rotating about a vertical axis. Next easiest thing to come up with are what the values are for a and b, our bounds. We would integrate from the lowest y value our region touches, so 0, and integrate to the largest value our region touches, so y equals 2. So our a and b will become 0 and 2. And now we have to determine the radius. In any volume of revolution problem, the radius is always measured from the axis of rotation. So that's really important. Let's write that down. So radius is always measured from the axis of rotation. Okay. So because of that, I'll start at my axis of rotation, which is going to be some arbitrary y value, something between 0 and 2. Because that's really what this integral is going to do, is it's going to feed into this expression values of y starting at 0 and continuously increasing to 2. So we'll start at some representative y value, and if we measure this distance, whenever we measure anything tethered to the y-axis, that is allowed to be called x. So the radius is x, but because we are rotating about a vertical axis, and that means our integral is with respect to y, that means we have to rewrite this and get it written in terms of y. So the radius must be a function of y. So what is the connection between x and y on this curve? Well, this curve is, of course, x equals y squared. There you go. So the radius is actually y squared. So 0 to 2, y squared dy. There you go. That's set up. So to integrate this, of course, we would power rule, so pi over 3, y cubed between 0 and 2. This would evaluate to 8 pi over 3 for the volume.